Among the characterization techniques for organic compounds, mass spectrometry was a little unusual in the way it operates, because it's one of the rare techniques that does not use electromagnetic radiation as its principle. And most of the other spectroscopic techniques that we're going to talk about use electromagnetic radiation. And so that's why this introductory subtopic will deal with electromagnetic radiation and changes that electromagnetic radiation causes in different classes of molecules. And then we'll delve into the first spectroscopic technique that uses electromagnetic radiation, infrared spectroscopy. So electromagnetic radiation is really, literally all around us. So visible light that we see is a form of electromagnetic radiation. The harmful UV light, which damages skin and can kill cells, is also another form of electromagnetic radiation, just a little more highly energetic. X-rays are a form of electromagnetic radiation. Microwaves that we use in our ovens as well. Radio waves or TV waves that are used to transmit information are a form of electromagnetic radiation as well. And so the big difference between these different kinds of electromagnetic radiation is their energy, which is related to the frequency of this radiation, or it is inversely related to the wavelength lambda. And the use of frequency and wavelength comes from the fact that electromagnetic waves have both particle and wave properties, and wave properties are characterized by frequency and wavelength values. In this case, the waves, the oscillation that we're characterizing in electromagnetic spectrum are pretty abstract. They're actually oscillations of vectors of electric and magnetic field. But they are characterized by this frequency and by this wavelength. And according to their corresponding wavelengths, different types of electromagnetic radiation are sorted and named differently. And so we're going to introduce you to that electromagnetic spectrum by starting with the most energetic rays, and these will be gamma rays. Their wavelength is very short, which means that their energy is very high. And so this is at 10 to the minus 6, 10 to the minus 11 meters. They're followed by X-rays, which are still highly energetic, but not quite as energetic, 10 to the minus 11 to 10 to the minus 8, followed by then different kinds of UV light. So this is ultraviolet light, 10 to the minus 9 to 10 to the minus 7 meters. And ultraviolet means that it's above violet, which means that within the visible spectrum, which is the next type of electromagnetic radiation that's following, the violet light has the highest energy. Right? And visible spectrum is actually a very narrow region of the spectrum which is able to cause a response in our optical nerve, and we're able to see this light. And visible spectrum also goes through a spectrum of visible colors, starting with violet and then going through blue and so forth, and then ending with red, which is the lowest energy visible light. Even below that is the infrared light, IR light, which is again slightly lower in energy. This is 10 to the minus 6 to 10 to the minus 3rd meters. You'll notice that with visible light I made an exception and expressed this in nanometers. And 1 nanometer is 10 to the minus 9th meter, so this all fits in. But the nanometers are just more commonly used when dealing with visible light. So, I mean, of course, it applies to any other type of light equally well. Going even further to lower energies, microwaves follow IR light, and microwaves are about 10 to the minus 3rd to about 1 meter in wavelength. After that comes the radio, and you'll notice that FM and AM radio frequencies, if you listen carefully, they'll be 94.3 megahertz or something like that. That is basically the frequency of that light. And from that, I would urge you actually to do this exercise and calculate the wavelength of that light. But if you do that, you'll see that the wavelength is somewhere on the order of meters, so it's between 1 and 100 meters. for FM and AM radio, and those are the ones that we're using the most. If you go even further down, the long wave radio, and I think you can still get this, but not many people listen to it. This long wave radio used to be something that Voice of America, Radio London, would transmit to the territories occupied by Germans during the Second World War. This long wave radio actually has wavelengths on the order of hundreds, about 10,000 meters, so it's on the order of kilometers already. And following even further are the TV waves, which are even higher. Okay. Now, why am I telling you all this? Why is this important? Well, the thing that makes light so relevant for our studies is that light interacts with matter. And different types of light interact with matter in a different way, causing different classes of changes. So that's one important thing. When we shine light onto a molecule, something will happen to that molecule. And the other important thing is that light is easily analyzed and quantified. So we can easily measure even a tiny decrease in the intensity of light, and we can quantify that. And then we can correlate that change in the intensity of light with the change that occurred in our molecule upon excitation with that light. And so that's why it means that we use light as an analytical tool in chemistry. Okay? Now, as I mentioned, different kinds of light cause different kinds of changes in matter, right? And so let's now review what kind of changes the different kinds of light cause. And so let's start with the most energetic gamma rays. They're so high energy that they basically break chemical bonds and thus destroy molecules. So if we're going to put in a scale of destructiveness, they will be high on top. And so they're not used very much because they will just break up everything. Gamma rays actually are a form of radioactivity, and they're very high energy is what makes them harmful. Okay. Following gamma rays are X-rays, and they're slightly lower in energy, but it's still very high in terms of chemical changes. And so what they do is they excite 1s electrons with very large energy. So what they basically do is they take the lowest lying, the most stable electrons in the molecule, and then they excite them to the highest lying orbital, meaning that they give them a huge energy push, which is corresponding with the high energy of X-rays. And all of this can be used, and it's actually useful in some kinds of spectroscopy. In organic chemistry, it's not used very much, and so we can basically ignore this for the time. Moving now to even further lower energies, UV rays already begin becoming interesting for us because they cause the electronic transitions. For example, we've seen when we talked at the beginning of the course, we talked about sigma and sigma star orbitals. So the T bonding orbital has a corresponding anti-bonding orbital, which is high in energy. UV rays typically will excite something from a pi orbital to pi star orbital. So will cause electrons from an already relatively highly lying valence orbital to excite to a little bit more to an anti-bonding valence orbital. And so this is something that allows us to characterize pi bonds quite well. And this will be useful in our discussion in the next half of this course, Chem 33-32. Okay. Visible light basically does the same thing as UV light. As we said again, Visible light is sort of this category which is quite subjective because it's the only light we see, and that's the only reason why we classified it here. But in terms of changes, UV visible is basically often considered one region because they both cause electronic transitions. And as you can also probably guess, that many things that we see as colored, like flowers or carrots, they are caused by these electronic transitions upon being hit by UV light or visible light. Going even further down is the IR light, and this light is slightly lower in energy than UV and visible, and so it's not able to excite electrons to complete a different orbital, but it can cause stretching or bending of chemical bonds. And IR light thus constitutes the basis of the so-called vibrational transitions, and IR spectroscopy is oftentimes called as vibrational spectroscopy as well. Going even further down, we'll get to microwaves. Now microwaves don't even have enough energy to excite vibration, and so they just cause rotations around chemical bonds. And as we've seen in our discussion of conformational isomers, stretching a chemical bond is relatively hard because chemical bonds sort of like to have certain equilibrium length, and if you stretch them a little further out, they will resist that. Whereas rotations, in many cases, is not too highly resisted, and so this rotational spectroscopy requires less energy. Now going even further lower in energy, we'll get to radio waves. And radio waves don't even have enough energy to do this, and so they cause actually a very small change in nuclear spin. So they don't have anything to do with electrons. Okay? And this change in nuclear spin seems like a pretty irrelevant thing, but it turns out that this changes in nuclear spin are actually very sensitive to the electronic environment around them, and they actually constitute the basis of NMR spectroscopy, which is the most powerful technique to use in organic chemistry. And so even though it's a very tiny and apparently relevant effect, this constitutes the basis of the most important technique that we will use. So in organic chemistry, we will use IR spectroscopy, and we'll talk about it immediately following this subtopic. And radio waves constitute the basis of NMR spectroscopy that we'll cover in the lectures immediately after this one. One other class that is also used is UV visible spectroscopy. We'll talk about this in Chem 33-32 when we start talking about conjugated systems and their characterization. In the next subtopic, we will get right into the IR spectroscopy.